These are your visual notes or your video notes for the non-Mendelian traits, sex-linked traits, and multiple allele traits. So let's go ahead and start on page 22. There we go, page 22. And we'll start with what are called non-Mendelian traits. So basically, Mendel got really, really lucky when he looked at pea plants. The traits that he looked at happened to work out to be dominant and recessive according to the rules that we've been going on in all of his monohybrid crosses and even in the dihybrids that we've been doing so far. But there are a lot of other kind of blending patterns of traits that are not simply if you have the dominant allele, then you have the dominant phenotype. So let's look at some examples. So this first example is called incomplete dominance. So what you're going to see is two different letters here, and it's not because we have two different traits. It's because both traits are equally, kind of equally dominant. So when you see two different letters like this, and they're both capital, you know that this is a non-Mendelian trait. So let's look at it and see what happens. Capital R is for red, capital W is for white. Notice there are no recessive alleles, therefore there are no lowercase letters. Both red and white are dominant to some degree. So if you're homozygous for the red alleles, you are red. If you're homozygous for the white alleles, you're white. But the incomplete dominance aspect comes into play with the heterozygous individuals. So if you are heterozygous, you have one of each allele, you are pink. It's a physical, kind of almost like a literal blend of red and white. And that's called incomplete dominance, this blending of the phenotypes. So let's go ahead and do an example. Cross a red snapdragon, which is a flower, with a white snapdragon. Well, if you're red, you must be homozygous R. If you're white, you must be homozygous W. Again, no lowercase letters. These are all capital letters. And every single possible offspring is going to be pink. So 100% RW and 100% pink. So that's incomplete dominance. Let's look at codominance. This is kind of the other option. So same thing, there's no recessive alleles, therefore there are no lowercase letters. Your two kind of dominant alleles each get a capital letter. So B is going to get us black feathers in this chicken, and W will get us white feathers. So if you are homozygous for black feathers, you are capital B, capital B. Capital W means you're a white feathered chicken. And if you have one of each allele, you're heterozygous, notice that you're not gray. If this were an incomplete dominance inheritance pattern, you'd kind of get a mix of these and get like a grayish hue. But you don't. You get individual white and individual black feathers. So rather than a blending of the traits, both colors, both phenotypes show up. This is how you can get spots. This is how you can get, like if you have a breed of dog or something, or a cat, and you have different colors show up on different areas of the animal, it's because those traits are co-dominant rather than a blending of the two. So here, if you have a black and a white chicken, the Punnett square looks, honestly, it's pretty much the same Punnett square with just a B rather than an R. So we'll fill this in, and 100% of your offspring are heterozygous, but since this is a codominant trait, rather than getting gray, we're going to get, you can say spotted, you can say speckled, you can pretty much describe it however you want. Spotted black, I'm going to specify that it's spotted black and white. But that's it. It's pretty straightforward. And anytime you have a problem where you're like, okay, well, is my trait codominant or is my trait incomplete dominant? You're going to have to pay attention to the vocab. Pay attention to see if they're talking about blending traits, see if the heterozygous condition is like a mix of the others, or see if the heterozygous condition has both characteristics simultaneously. And that'll tell you if you're dealing with a codominant trait or an incomplete dominant trait. Other times we might just flat out tell you in the word problem if we're feeling generous. We'll do the practice questions in class, so I'm going to go ahead and keep scrolling. Let's go down to page 25. All right, 25 is a multiple allele problem. So we're going to focus on blood type. Multiple alleles means that you don't have just a dominant and a recessive or perhaps two dominants. There are actually three different alleles here. Two of the three are dominant. So the blood types A and B are dominant, and the little I here is the recessive allele. And you'll notice that the notation has changed. We don't just write the letter A, the letter B, and a lowercase I. We have like this superscript. It's like a capital I to the superscript A and a capital I to the superscript B. Those are your dominant alleles. And your recessive allele is just a lowercase I. So this table is, you don't have to memorize it by any means, but I have a feeling you probably will by the end of the unit. If you're homozygous for blood type A, that means both of your alleles are A alleles. Or you could be heterozygous for type A, in which case you have one dominant allele and one recessive allele. The same is true for type B blood. You can be AB, have type AB blood. That means you have one A allele and one B allele. Notice that this is codominant. So it's an example of codominance embedded within a multiple allele problem. Both the A and the B blood type show up simultaneously in the same person. That's what having AB blood means. And then here, if you have both recessive alleles, you have type O blood. There is an additional, what's called a factor that you can have called the RH factor. And in addition to having this blood type, you can also either have the RH factor or not. And you can be either positive for it, meaning you have it, or negative for it, meaning you don't. So there's a little bit more info about blood types that we're not going to cover. This is just the basics when we talk about multiple alleles. So 1 and 2 are actually pretty easy. I'm going to skip down to number 3 on page 26. So it says the father is type A heterozygous. I'm going to go ahead and just put that in here. If you're type A heterozygous, you must have an A allele. But you're heterozygous, which means your other allele is recessive. So let's put dad over here. And mom is type B heterozygous. So she must have a B allele, but she's heterozygous, so her other allele is recessive. And you do this Punnett square just like you would do any other Punnett square. There's no tricks simply because there's 3 alleles. Nope, it's all the same stuff. So fill this in. And what you're going to see based off this is that there's a 1 in 4 chance that you're type A. You'd be heterozygous, but you'd still be type A. So I'll say 25% chance for being type A. There's your chance for being B. Again, you'd be heterozygous for type B blood, but you'd still be type B blood. So 1 in 4 is 25%. Same thing for type AB, and same thing for type O. So I picked this problem because all of the possible blood types exist in the offspring, right? You could have any blood type offspring if your parents were like they were in number 3. So the rest of these, numbers 1 and 2 on page 25, and the rest of all of the blood type problems we'll do in class, so I'm going to keep going. There are no questions for polygenic traits. There's no practice problems or anything. Just note that the vast majority of traits in any organism, especially your mammals, your higher order animals, are usually due to an interaction between two or more genes. Not just alleles, genes. And a lot of time these genes are on different chromosomes. So some examples of traits that are polygenic are skin pigmentation. You can get a wide variety of pigments, height, anything that kind of has called a normal bell curve distribution, where you have a lot of people kind of in the average, and then as you move out to either extreme, you have less people, or it's less frequent. These types of distributions are usually caused by multi-gene traits. But again, there's no problems for it, just to make you aware that they exist. All right, last page here is page 29. We're going to talk about sex-linked traits. To talk about sex-linked traits, we first have to talk about the sex chromosomes. So in humans, remember you have 23 pairs of chromosomes. The first 22 pairs are called autosomes. The 23rd pair, the final pair, are what are called the sex chromosomes. And you are probably familiar with this. Chromosomal males are XY and chromosomal females are XX. So down here, we're just going to copy that. So in a father, you could, as a male, have sperm that have an X chromosome in them or that have a Y chromosome in them. Those are the two possible types, right? If you're a female, the two possible types of eggs that you can make are going to have X chromosomes in them. And I know in meiosis there are technically 4 gametes every time you go through meiosis, but these would just be the same. So you'd have 2 X's and 2 Y's per meiotic event. But just to simplify things, we're just going to draw them once each. So mom's eggs will be on top. Hers have to have an X chromosome in them. Dad's sperm on the side here. One of them has a Y. So all of the possible offspring, again, you can just do this in a regular old Punnett square. And you can see anytime that a man and a woman have a baby, there's a 50% chance of that baby being a female and a 50% chance of that baby being male. So you can answer, actually you can answer all of these questions, which we'll do in class, so I will skip these. And we're going to go down to actually just doing a Punnett square with these traits. Because these are sex-linked traits. So think, as a shortcut here, sex-linked means X-linked. So if you're a female, a sex-linked trait just means that it's on your X chromosome. So let's say right here, you've got oops. I'm sorry, that's confusing. When I say X chromosome, the chromosome itself is not necessarily shaped like an X, and the Y chromosome is not necessarily shaped like a Y. The X chromosome is just a single line if it hasn't copied itself yet. So if you're female, let's just redraw this over here actually. If you're female, say that's an X chromosome, that's an X chromosome. If you have a trait on your X chromosome here, and you'll have a trait on your X chromosome here, so maybe this individual is heterozygous. Males, remember, they only have the X chromosome, so they'll only have one allele for that trait. The Y chromosome is much shorter. It's like a little teeny stump, and it doesn't even have the rest of the, well, I don't want to say the chromosome is empty, but it's just a much shorter chromosome. So females will have 2 copies of a sex-linked trait. Males only have the 1 copy of a sex-linked trait, and that means that males are affected by sex-linked traits much more often, and we'll talk more about this in class. But that's what sex-linked traits are. They are traits They are, with the genes, are only on the X chromosome, only on the X chromosome. And the ones that we're going to look at are color blindness, hemophilia, and male pattern baldness. I would commit those to memory. Those are the sex-linked traits that we are going to focus on. They are the most common sex-linked traits. Remember, only on the X chromosome, not on the Y chromosome. All right, so just to do a couple here. Normal color vision female. Well, you know she's female, so we're going to put 2 X chromosomes down. And she has normal color vision. Normal color vision, right? Well, color vision is a sex-linked trait. So she has to have at least one normal allele. By the way, the normal conditions are all dominant here. And she could be homozygous normal, right? She could have 2 dominant alleles, or she could have a recessive allele. She could be heterozygous. Remember that these are not incomplete. These are not codominant, nothing like that. No blending of traits here. This is kind of a different category. These are sex-linked, so really the only new thing is the fact that the chromosomes are in our notation. You'll notice it's kind of like what we did with the multiple alleles. You have like the chromosome and then the exponent, the superscript. It's kind of like that. So either one of these would get you a normal color vision female. Now here they tell you, okay, she is normal, but she's a carrier. So here they're specifying we only care about the heterozygous condition. And then you can keep going. Colorblind female would have to have 2 recessives because she's colorblind. That means there are no dominant normal alleles for her. Here's the interesting two. Normal color vision male. He has a normal allele on his X chromosome, but notice there's nothing on the Y. We're not going to put anything on the Y chromosome because sex-linked traits are only on the X. All right, so a colorblind male has a recessive allele on his X chromosome and nothing on the Y. And this is why males are more affected by sex-linked traits. If you're a female and you have a recessive allele, you have a backup copy on your other X chromosome. That's another opportunity for you to be quote-unquote normal, have a normal allele. But if you're a male and you have a recessive allele on your X chromosome, your Y chromosome is not coming to save you. There's no allele there. So all it takes is one allele to have that trait. That's why all of these are more common in men. And the other thing, here's the kicker. If you're male, where did that X chromosome come from? It came from mom, right? I mean, dad had to have given you the Y. He's the only one that had the Y chromosome. So the X must have come from mom. So sex-linked traits are passed down through the mom's side of the family and affect men disproportionately. So go ahead and finish these. We'll do these in class. We'll keep doing these in class. We'll do all of page 31 in class. And for number 12, I'll talk with you guys more about number 12 in class as well. So all the way down to page 32, and then you are going, we will stop in class. All right, so we will do up to page 32 together when I see you in class, and I hope this helped. I'll see you then.